Hi, I'm Akanksha, a PhD student at UMass Amherst, and I'll be talking about our latest research for highly accurate solar modeling using satellite data. This work is in collaboration with my PhD advisor, Professor David Arvin. Grid-connected solar capacity continues to grow exponentially at roughly a 20 to 30% increase per year. As we can see from the graph, from now to 2050, solar PV is expected to grow the fastest of all the renewable energy generation. Since all the solar generation is grid tied, this dramatic increase in the solar power is expected to place increasing stress on the grid, which must continue to balance the supply and demand. While solar cells ramp up and down almost instantaneously with the passing clouds, it may take anywhere from tens of seconds to days for the conventional thermal generators to activate. As a result, under large solar penetrations, utilities keep many conventional generators active as spinning reserve to offset any dips in the solar power, which is both expensive and highly energy inefficient. While batteries can mitigate some of this inefficiency, it's unlikely to get eliminated at the grid level. Thus, inferring solar output from widely available data sources is becoming increasingly important, and it lays a foundation for a wide range of solar analytics. Solar power is a well-known function of many static and dynamic factors like location, time of the day, cloud cover, temperature, etc. And there are many solar performance models available to infer the same. But the most significant error in the existing methods is inaccurate estimates of solar irradiance. One of the ways to estimate solar irradiance is by measuring the cloud cover as reported by the ground weather stations in the form of octas, where one octa is equal to 1/8 of the sky partially covered by cloud. As we can see from the graph here, the octas are very noisy and cannot capture the effects of complex cloud formations. These imprecise measurements in turn yields larger inaccuracies in solar modeling. A new opportunity came by the launch of the new range of satellites by NOAA in the late 2017s, the Geostationary Operational Environmental Satellite, or the GOES-R range. These satellites comes with new capabilities and much richer and wider set of data, which differs both from the high-quality ground monitoring stations and also the previous generation of satellites which it replaces. The spatial coverage is for every 0.5 to 2 kilometer square area across the US, while the data is released every 5 minutes. The special ABI instrument senses data in 16 different spectral bands of light. In addition to these, NOAA also releases numerous secondary derived products as well, like downward shortwave radiation or DSR. But it is unclear how to calibrate models for using these data for solar performance modeling. In this regard, we compiled a dataset of 29 solar sites, including solar generation data, octas, temperature, and maximum available multispectral satellite data from both the GOS 16 and 17 at 5-minute resolutions. We develop machine learning models to train both the local and the global models, where local models are site-specific models which require historical data to train. Global models are pre-trained models which can be applied on any new site from across the US. We also evaluated various variants of these ML models. We tried some basic machine learning approach on these multispectral channel data using the curated dataset we have created. The input to the ML model are channel data values which both directly and indirectly quantify the surface solar irradiance along with the temperature at the same time instant t. The output of the model is the solar generation at time t. We compare different ML models like support vector machines, regression, decision tree, and simple regression. A key benefit of our approach is its simplicity. A standard ML regression model is applied to a dataset composed of only 3 input features with no domain-specific knowledge. Our ML approach is entirely data-driven and black box, which is also able to implicitly account for the site-specific attributes like panel type, tilt, orientation, shading, etc. Our local ML models must be trained for each individual solar site, which requiring sufficient training data and cannot be applied to new solar sites with little data. To address this, we also develop a global ML model using the satellite data. Global models, once trained, can be applied to any solar site without retraining the model. In addition to these ML models, we also experimented with many model variants. While traditional modeling approaches only infer solar at 60-minute resolutions, our model quantifies the effects under 5, 15, and 60-minute resolutions. We also quantify the effect of using visible light versus all the 16 channels. And we also quantify the effects of using multiple satellites, that is, combining distinct information from different angles. The key result is that our ML-based channel model significantly improves the accuracy, reducing the error by almost 50% over the cloud cover approaches and satellite-derived products like DSR, which are released by NOAA. Such accurate estimates lay a foundation for future work in solar modeling and forecasting. Thank you for listening.